So let's go through this activity where we were matching pretty common function families with the slope fields that they generate. Let's see how you did. All right, so the first function there was y equals x. So y equals x is a linear function. It's not a constant function, but it's got a constant rate of change. So we should be looking at a slope field that's not flat, but is steady throughout its entire thing. And that is graph C looking like that. All right, so that's number one there. Function number two is y equals x squared. That's a standard looking parabola, uh, centered right there at the origin. It's got that left-right symmetry looking like that. So 2 is A. 3 is y equals e to the x. So this is an exponential function. This is one of those, I don't know, it was described as J-shaped, I suppose. It looks kind of like a J, but really stylized. So starts out flat, and then the further it goes to the right, the further it just kind of shoots up into the sky. And so that is function f. 4 was y equals 1 over x squared. So 1 over x squared, you might not be completely familiar with that function, but let's think about it for a second. So it's got, let's use some beginning of the year vocabulary. It's got a vertical asymptote, a straight up and down asymptote at 0. So it's looking that way. Since it's x squared in the denominator, it's going to be an even function. So it's going to look the same on the left and right hand side of the y-axis. And the other thing is that when x gets bigger and bigger, you're dividing 1 by a bigger and bigger number. So as x gets large, y should be getting close to 0. And so looking at all of these graphs, I hope you are seeing that I was describing the graph of function d. All right, so 4 is d. 5 is y is equal to x cubed. This is an odd function, which means it's going to be symmetric about the origin. So it's not going to be the same sort of thing. This is also an odd function, but the slopes are going to differ through it. All right. There are a couple functions that meet that criterion, but what we're looking for is we're looking for h. So it's a function that looks like this. All right. And it gets steeper and steeper the further you go to the right. All right, so you might have been teased by I there, but we'll see I when we get to it. All right, 6 and 7 are our trig functions, sine of x and cosine of x. So we should be looking for wave-shaped functions, and so that look like b and e. So let's think about which one is which. So remember that the sine function is an odd function, which means that at 0, it's halfway through its rising point. So sine of x looks like this. All right, so sine of x is b. Cosine of x at the y-axis, it's at the top of it's having a peak there. All right, so this is cosine here with the peak at 0, and sine is at its midpoint at 0. All right, so 6 was b and 7 was e. 8 was y equals the absolute value of x, and I'm sorry, not the absolute value, the square root of x. And so one thing about the square root of x is that this is a function that's not defined for negative values of x. So that really points us to j. So here's what the function of y equals the square root of x looks like, something along those lines. All right, so 8 is j. 9 is y equals 1. So this is a constant function. So this is not just a constant slope field. C was a constant slope field, but G is going to be not just constant, but it's going to be flat. So this is going to define only constant functions. So 9 was G. And the last one was tangent of x. And so tangent of x looks like this. So it's a little bit different from x cubed in that x cubed at the origin, it's flat. All right, so you've got an inflection point there at the origin. For tangent, it looks like this. All right, so when you get to the origin, it's going to be at a 45-degree angle. And the other thing about the tangent function is that it has lots and lots of these asymptotes. So that's why you've got a function that looks like that. All right, so here was the key for that. So we've got C, A, F, D, H, B, E, J, G, and I. All right, so hopefully you got most of those right. And hopefully if you were a little bit confused by these, you did a little bit of research on your own and got stronger with these basic function families. All right, so we've been talking, it's one of the things we've been studying all the way up through calculus. And you may have wondered at the time, why are we studying exponential functions? Why are we studying trig functions? What's important about these? And what's important is that these are functions that model some real world phenomenon. And so when people get into studying those real world phenomenon, they want to be able to do calculus to it, to study the rates of change of these functions. So really most everything we study in high school math, if you come to me and say, why are we bothering learning this? I would probably say you get the payoff in calculus. And so here you are looking at these standard function families and how they look as their slope fields, how their derivatives look, and how the functions behave. And we can have these much more mature discussions than we were able to have even just 7-8 months ago, because now we've got all of this calculus under our belt. In the next video, we're going to look at a few extra sample problems talking about slope fields, and then that's all we'll have to talk about for this subject.